Hey guys, hope everybody's doing okay. What we're going to do today is continue with our acid-base equilibrium unit and talk about something called buffers. Buffers are solutions that contain certain components, and when they contain those certain components and you add an acid or a base to them, it helps resist pH change. So on the screen in front of you, you can see that on the top here, I have an unbuffered solution, maybe just some distilled water. Even though the starting pH is a little low for that, but it's some solution with the pH of 5 that doesn't have the components that are required to create a buffer solution. Okay, so let's take a look at what happens with my initial pH of 5, and I'm going to add an acid to that. So we should expect our pH to decrease when we add an acid, and it does. So we can take a look at it, and our pH drops to 2. If you add a base to it, we should expect our pH to increase, and it does. It goes up to 12. So you can see that's a pretty drastic change in pH. We have an initial starting point of 5, and adding our acid goes down to 2, and adding our base goes up to 12. Let's see what happens with a buffered solution. So we'll define this in a little bit, but if I have a buffer solution, which is a special mixture of certain solutions to make my overall solution, you can see that I'm starting out at a pH of 5, and I add an acid to that, and I go down to 4.98. So that's a much less drastic change in pH than the unbuffered solution. Same thing happens when I add a base. I'm going to go up, but I'm only going up to 5.02. All right. So you can see that we have a minor change in pH with our buffered solution compared to our unbuffered solution. So let's take a look at just a common buffer here, which is a buffer that consists of carbonic acid and the bicarbonate ion. So you can see that on the screen here. And that's a buffer that's present in blood plasma. And that helps maintain a pH of 7.35 to 7.45, which is necessary for enzymes to work. So really, really important stuff are buffers, obviously for you and your body, but also for some other things in nature as well to help prevent effects of maybe acid rain. If you have a buffer solution in your like a lake or a pond, that could help there. So let's take a look at what they are. Buffers minimize pH change when you add an acid or base to them. Here's how they're made. That's in red up here. So it's pretty important stuff. Buffers can be made by placing a weak acid in solution and adding its conjugate base. All right. So this is key stuff here. It's weak acid, conjugate base is what you want to look for a buffer solution. All right. We're going to see how it works here on the next slide or two. The example we're going to look at is mixing hydrofluoric acid, HF, with sodium fluoride. That's going to result in a buffer solution. So we have our hydrofluoric acid solution, our sodium fluoride solution. The combination of those, or both of those in the same flask or beaker, is creating a buffer. So our initial pH is going to be pretty acidic, right, with our hydrofluoric acid. Then if I add some solid sodium fluoride to that, sodium fluoride is extremely soluble, so it's going to completely dissociate. It's going to do that, dissolve pretty readily in our acid solution. NaF dissociates into Na+1 and F-1 ions. So you can see our dissociation equation for hydrofluoric acid. If I increase my fluoride concentration, right, by adding the NaF, due to Le Chatelier's principle, right, we increase the concentration of a product. That increases Q, which would shift the reaction to the left, and create even more HF. All right. So what we end up having in our beaker is a lot of HF, okay, undissociated HF, and a lot of the fluoride ion as well, okay. And that fluoride ion is coming from the soluble salt that we added here. So we have lots of our acid, our weak acid. We also have lots of our conjugate base, which is exactly what we need for a buffer to occur. So we talked about that a little bit. I'm going to draw a beaker, or have a beaker on the next slide, and we're going to write down what happens when an acid or a base is added to that so you can see how a buffer works. Okay, here it is. So we have our acid solution, our hydrofluoric acid solution. We have our dissociation equation here. And remember, not much of this dissociates, so we're very heavily favored to the reactant side. All right. We do have a little bit of H plus 1 and F minus 1 in that solution. Not a lot, though, so I don't have it shown on the screen here for you. Now let's add our soluble salt, which is NaF. Dissociates very well because sodium is a group 1 metal. Group 1 metals are always soluble, so that's what we have there. And it looks a little congested in the beaker here. Okay. We're going to get rid of the sodium ions. They end up just being spectators. If you remember from our hydrolysis of salt lesson, sodium is a group 1 metallic ion, and they are negligible in terms of their acidity or basicity. So let's just get rid of those and just take a look at what we have in our beaker. So I have one other equation here for you. I have NaF yields, because it completely dissociates, right? Na plus F minus. Okay? So you can see lots, and again, the Na plus is our spectator. So we have lots of fluoride and lots of hydrofluoric acid. Let's see what happens when we add an acid or a base to these things. So that's what we have here. So what happens when a base is added to our buffer solution? Well, a base could be something like sodium hydroxide or potassium hydroxide, or maybe some type of carbonate. Let's just pick a hydroxide. Let's say we added maybe potassium hydroxide to that. So our base is going to be KOH. I'm going to add KOH to this beaker with these ions in it. Okay? We're really going to focus on the hydroxide ion. Okay, K plus 1 is the same as Na plus 1. It's negligible, right? It's basically a spectator, not taking part in much. So you want to ask yourself, when the hydroxide is added to this beaker, what's it going to react with? Is the hydroxide going to react with the fluoride? That wouldn't make any sense, right? How is an OH minus and an F minus going to react? It's not. So the OH is going to react with one of our acid molecules. All right? So let's show what that's going to look like. So we have OH minus plus HF yields. Now the hydroxide is going to scope out the hydrogen, okay? We're going to make water. And you're left with your fluoride anion. So this is really cool because you have your hydroxide and you're going to add your hydroxide to the beaker. That would normally make our pH rise pretty rapidly, right? Because it's OH negative is a strong base, the hydroxide ion. But look what happens. We have our hydroxide. We add it to the beaker, and it ends up reacting with something. So what we end up with is water, which is neutral, and fluoride, which is a basic anion, but it's obviously weak, okay? So you go from having hydroxide, the potential of having hydroxide, which is a strong base, to now having neutral water and your fluoride anion, which is a weak base. So the pH change is going to be minimal here. It'll still increase when you add a base, but it's not going to increase by much. Let's take a look at when we add an acid. An acid could be hydrochloric acid, nitric acid, whatever. Typically you think of an acid as H plus though. All right, so now I'm going to add H plus. I'm going to pour some acid in here. What's going to happen? Well, the H plus from, like, say, nitric acid isn't going to really scope out the hydrofluoric acid, the HF. That wouldn't make any sense. So what it is going to do, though, is scope out the fluoride ion. So it's going to come over here. All right? So H plus F minus yields HF. Okay, let's take a look at what happened here. Obviously, H plus, consider that strong acid. Again, if you have just H plus floating around in this beaker here, you're going to have, your pH should go down by a lot, right? Because H plus is extremely acidic. But what you end up with is H plus combining with F minus, that conjugate base of HF, that basic anion that we got from adding the NaF solid into here. Now it reacts with the hydrogen ion and creates HF. which is a weak acid. So when you add an acid, your pH is still going to decrease, but it's not going to decrease by as much. So H plus would cause a rapid decrease in pH, and that's what happens in an unbuffered solution, like we saw on our first slide of the day. We saw a big time drop in pH. But when it combines with the fluoride to make HF, we end up with a weak acid. So there is a drop in pH, it's not as drastic. Okay, here's another example that you can try. This is a buffer solution with sodium acetate and acetic acid. So acetic acid is HC2H3O2, and sodium acetate is NaC2H3O2. So we do have a buffer solution here. You have your weak acid, acetic acid, and you do have your conjugate base. Now, sodium acetate dissociates completely, right? The salt that you add for your buffer solution, it has to be really soluble so it can dissociate. We don't have to worry about the Na+1, and what we are going to worry about is the acetate ion. So you have a beaker with lots of undissociated acetic acid and lots of acetate anion. Okay? So right, what happens when you add nitric acid, the formula is HNO3. But again, all we're worrying about here is adding the H+. And let's see if we add potassium hydroxide. Or again, we're just going to focus on the OH-. Okay, so let's take a second and write those. And we'll see if we get them right or not. If you take a look at the first one, we're going to add nitric acid, which is just H+. I have it on the next slide here. This is just another way to write the acetate ion here, and then the acetic acid formula here. So it's just another way to write it. So it's still C2H3O2-, and here it's still H, C2H3O2. Okay? So let's add an acid to that. The acid is going to react with the anion, the acetate anion, and what you're going to do is end up with acetate ion plus H+ yields acetic acid. So you can see the anion concentration will go down a little bit from where it started, and the acetic acid concentration will go up a little bit. So the pH is still going to drop, but not by much, okay? Because instead of having pure H+ in solution, you're going to end up with the acetic acid instead. Hydroxide is going to combine with the other component. That will combine with your acetic acid. So you can see your acetic acid right here, combining with hydroxide, creating water and your acetate ion. So again, you end up with more acetate ion in solution right here, and a little bit less acid. So you are going to have an increase in pH, but it is not going to be as drastic as it would be if you just had the hydroxide ion in solution. So the moral of the story here is your hydroxide from the base that you add is going to be combining with your weak acid that's in your buffer. And if you add an acid to your buffer, that is going to combine with the anion, that basic anion, from your soluble salt that makes up your buffer. I'm not going to talk about this too much here, but there is a limit to how long a buffer could withstand that pH change. That's called buffer capacity. All right. So buffer capacity refers to the ability of a buffer to resist pH change, and there are ways to improve that. So buffer capacity is going to increase or improve as the concentration of your components, which is the acid and the conjugate base, as that increases. Okay? That's what this chart shows. If the concentration of your acid and conjugate base is, let's say, 1 molar, look, you're going to have a little tiny pH change, okay, just a little bit, like, less than a tenth here, right? But if you look at down here, let's look at this one. If your concentration of your components is really low, 0.030 molar, look at the range of pH you'll have, like that pH change as you add acid or base. It's a much bigger pH range and change compared to the small little change you're going to get from the higher concentrations. So the higher concentration, the better. That means the more acid or base you can add, and the less your pH is going to differ or fluctuate when you add that. And a couple other things about this: you want to have a pH of about between 6 and 8 for a good buffer. All right, so that should be a good little range to start out with there. And this is also key here. You can see that in a little bit. Fairly equivalent concentration of acid and conjugate base. You want to buffer your acid and base if it's added relatively equally. So if you have a fairly equivalent concentration of acid and conjugate base, it'll help buffer the acid and base relatively evenly. Okay, so the pH of your buffer, the starting point, and the buffer capacity, how it withstands a pH change, are obviously two different concepts. Okay, quick little review here on what makes up a buffer. You could go through these as well and see if these are buffer solutions or not. So one of the really key important things here is to identify if you have a buffer or not. And then you could take it from there. So again, you're looking for a weak acid and its conjugate base, which is going to be the negative anion. So let's take a look at letter A. You have hydrofluoric acid. That's HF. Is that a weak acid? Absolutely. So we're 1 for 1. And potassium fluoride is KF. Extremely soluble, right? So it's going to dissociate into K plus 1, which we're not really worried about here, and F minus 1. So this is definitely a buffer solution. You have your weak acid, HF, conjugate base, F minus. So letter A is a buffer. Take a look at letter B. First thing I see is chloric acid. I write the formula for that. That's HClO3. And automatically my brain goes to strong acid. All right. So chloric acid is one of our 7 strong acids. So buffer solution is not. Okay. Because it's a weak acid and it's conjugate base. Don't be tripped up here or confused or kind of fooled by letter C. You have ammonia, and we should know that by now. That's NH3. You're going to say, well, that's a base. I have ammonium bromide as my other component. Well, let's see what that is. Ammonium bromide is NH4, Br. You should recognize that NH4 is ammonium. It's the ammonium ion, obviously. It's very soluble. So this is going to be completely soluble in solution. So I'm not going to worry about the Br right now. And I'm going to focus on the NH4 plus 1. Okay? You should recognize from your hydrolysis of salt lesson, NH4 plus 1 is an acidic cation. So that's a weak acid. And guess what? Ammonia is the conjugate base. If NH4 plus 1 donates a hydrogen, we're left with NH3. So that's a buffer. Letter D gives you a little hint here. It says acetic acid and sodium hydroxide. At first you might think not going to happen. Let's take a look at it. Acetic acid plus sodium hydroxide produces water. That's water. Okay, and sodium acetate. Okay, now, do we have a buffer solution? We actually do. Here is your weak acid, okay, acetic acid, and here, remember, this dissociates the sodium acetate. So that is Na plus 1, and you're left with C2H3O2 minus 1. Well, guess what? That is your conjugate base. All right? So this does occur. I mean, we just have to make sure we don't add so much NaOH that the acetic acid completely reacts. So you need the acetic acid and some NaOH, so we end up with some product, which is our conjugate base, and of course water. So yes, that's a buffer. Last one, sulfurous acid, H2SO3, calcium sulfide, CaS. Definitely not a buffer. You do have a weak acid, H2SO3, but your conjugate base would be SO3. Your conjugate base would be HSO3 minus 1. And that's not what we have. We have the sulfide ion, so it's not going to be any good. Okay, Moving on to part 2 of this, which is a little bit shorter than part 1, we're going to do some calculations with buffered solutions, and I'm going to help you derive something called the Henderson-Hasselbalch equation. So you don't need to know how to derive this, but if you do look at the next couple slides, so you can see how we do. So you have a weak acid dissociation. Okay, we wrote that a million times. Write a Ka expression. We know how to do that. Rearrange the Ka expression a little bit. Take the negative log of both sides, and here's where we're at. We should recognize some of this. Negative log of H3O. Remember, H3O plus is the same as H plus. So negative log of H3O plus or negative log of H plus is pH. Negative log of Ka is pKa. And then your HA is your acid, and the A minus is your base. Okay, so that's what the Henderson-Hasselbalch equation, like some of the components are. Let's simplify it. So plugging in pH and pKa, from where they, just replacing the negative log Ka and negative log of H plus with those, we end up with this. Rearrange it a little bit more to get pH alone on the left-hand side, and you end up with pH equals pKa plus log of conjugate base over your weak acid. That is your Henderson-Hasselbalch equation, and that is the key to a lot of buffer calculations. Okay, don't use it for anything else. It's just for buffer solutions. And there's a little shortcut here. If your concentration of base and acid are the same, your pH would be equal to your pKa. So if you end up with equal amounts or equal concentration of base and acid, you end up with log of 1. A log of 1 is actually 0. So you end up with pH equals pKa. Just a little logarithm stuff right there. Okay, let's move along to some practice problems. Before we do that, sorry, one last comment to make here. This is obviously only good for buffers, all right? It's also meant to be used with initial concentrations. That is so important here and actually beneficial to you because that means no icy table. Usually we make an icy table to get equilibrium values. But if this uses the initial values, we don't need the equilibrium values, so don't worry about it. You could do an icy table to solve some of these buffer problems, and that would involve the common ion effect, which is what a previous lesson was on. But if you recognize that it's a buffer and you can use the Henderson-Hasselbalch equation, it will save you a lot of time and energy here. So you're looking for the word buffer or recognizing a buffer, pH, and some initial concentrations, and you're good to go. So, first example, what's the pH of a buffer that is 0.12 molar in lactic acid, and I gave you the formula, and 0.1 molar in sodium lactate. Students get confused by this because they're like, I never learned any of these ions, and you're right, but who cares? You don't need to know them. What you do need to know is lactic acid is not strong, okay? It's not one of our 7 strong, so it's one of the other bajillion weak acids that are out there. So lactic acid is HC3H5O3. If you lose a hydrogen, you lose that acidic hydrogen in the beginning, you end up with C3H5O3 minus. All right, so sodium lactate would be Na C2, or Na C3, let me rewrite that, C3 H5O3. Okay? I was thinking of acetates. That's all we've been using so far. So NaC3H5O3, it fully dissociates because sodium is a group 1 metal, so you end up with C3H5O3 minus. That's what the sodium lactate is providing. So we know we're going to have a buffer solution because we have our weak acid, and here's our conjugate base. So let's write the equation that we end up with. C3H5O3 yields H plus C3H5O3 minus. That's the dissociation for lactic acid. We know we have lots of this because it's a weak acid. Look at that small Ka value. And I know I have a boatload of this from the sodium lactate. Okay, so I normally wouldn't have a lot of that, but because the sodium lactate is added to this, I now have it. Okay. If this just said you have lactic acid, you couldn't do this. It's not a buffer. You need the lactic acid and that source of lactate ion, okay, that anion as well. So I know I have a buffer solution. Let's solve it. I have a buffer solution. I have initial concentrations, so we're good to go. Equation, right here, Henderson-Hasselbalch equation. I do like to put in the formula for my conjugate base and weak acid. You can see that here and here. And just plug everything in. Pretty easy. So negative log of your Ka value, that's what pKa is, negative log of Ka, plus log of 0.1 over 0.12. Make sure you, that whole thing's in parentheses, do the log of that fraction. And you end up with 3.85 minus 0.08, and you get 3.77 for your pH of that buffer solution. Okay? A little low, right? Our ideal range is between 6 and 8, but it's still a buffer solution, just has a low starting pH. That's it, guys. That's all you gotta really do. Take a look at the next one. It says a buffer is made by adding 0.3 moles of, here we go, acetic acid. So assume that again. And 0.3 moles of sodium acetate to enough water to make 1 liter of solution. Ka value is 1.8 times 10 negative 5. Calculate the pH. We know we have a buffer because it tells me, but again, we recognize this. Here's our weak acid. Here's our conjugate base. All right. Because the Na and the acetate dissociate, so you get C2H3O2 minus 1. Both of them have the same number of moles, all right? And you're in a 1 liter solution, so you know, just for the heck of it here, we have 0.300 moles per liter, per 1 liter, obviously, because it's a 1 liter solution. So both of these have an initial molarity of 0.300 molar, all right? And go back to one of our shortcuts a couple slides ago here. If the concentration of base equals the concentration of acid, then the pH is equal to the pKa. So we have that situation here, all right? Both of my acid and base have the same concentration, so my pH is equal to my pKa. So that's going to be equal to my negative log of Ka, which is negative log of 1.8 times 10 to the negative fifth. I believe that comes out to 4.74 for your pH of this buffer solution. Okay? You could have continued the Henderson-Hasselbalch equation. Okay? You could have had the concentration of conjugate base over acid. And there we go. .300 over 0.300. All right. So that's plus log of 1, which is plus 0. All right. So log of 1 is 0. So you end up with that. Okay. pH equals negative log of your Ka value plus 0. So that's why I just go right to the shortcut here. pH equals pKa if acid and base are equal concentrations. All right. You guys can try another one. You go to packet page 56 as part of your homework set, number 23. And this one involves you solving for something besides pH. So you could solve for a bunch of stuff here. Most of the time we want to figure out what the pH is, but sometimes we know what the pH is, and we have a Ka value that we know as well. And we could find out like how much acid or base we need to create that buffer. So you have to undo your logarithm, which we've done earlier with pH and pOH calculations, and either solve sometimes for your base or your acid. Okay, so that's what that one is going to be about on page 56. So give it a try, check our work, and when we get into class, if you have any questions or concerns, we can talk about them and see how we're doing. All right, thanks guys.